So let's take a closer look at one of the millennial timescale process that's been looked at quite extensively, just to see in terms of the processes and the time scales. The bipolar seesaw is a good example of the abrupt climate changes, and not everything is understood, but a lot of work has been done. So the bipolar seesaw, coupled with the Southern Ocean heat reservoir to form the thermal bipolar seesaw. This is from Tom Stoker's own work. So the Southern Ocean, if you remember, is a channel, and it connects with the three oceans, Atlantic, Indian, and Pacific Oceans, and we have talked about it in the case of the thermohaline circulation. So obviously there is a close relation between the North Atlantic deep water formation and the slowdown of it or shutdown of it in terms of the heat transport and the temperature changes that happen in the northern hemisphere around Greenland specifically, and how that corresponds to a change in the Southern Ocean. Obviously ocean has to be involved because such changes don't happen through the atmosphere. There are various ways to understand that from physics, and if the ocean is responsible, then you have to understand that the ocean timescales are slow, as we talked about. So the observations give you a time scale of the relation between the Greenland temperature changes and Southern Ocean changes. So you have to explain what may be causing the links and what is determining the time scale. So those are kind of the issues. So if you have some process like the northward heat transport by the Atlantic meridional overturning circulation, which can have a rapid change, let's say due to sudden release of a pulse of fresh water from a glacial melt, water that has been held by ice dam. The ice dam breaks and there is a substantial amount of fresh water released into the Labrador Sea, North Atlantic, either from Greenland or from Lake Agassiz, as was argued for the Younger Dryas. Then there is some process which can create a jump, a shift in temperature in the northern hemisphere. So let's say the relation is through the South Atlantic North Atlantic bipolar seesaw, bipolar north and south, not the same word as the bipolar syndromes, but anyway, so that corresponds to Southern Ocean changes, and both are recorded in ice cores as we saw before. So the idea of just explaining that through the Atlantic meridional overturning circulation, and then providing various arguments to explain the time scales recorded in ice cores approximately works, but you have to explain some kind of a time scale of the heat storage in the Southern Ocean. So the Atlantic meridional overturning obviously transports heat from the southern hemisphere to the northern hemisphere, and this has a certain time scale, and if you reduce northward transport across the equator into the northern hemisphere, you are keeping more of the heat in the south. So colder the North Atlantic in this sense, less the heat transport coming into the North Atlantic, warmer should be the Southern Ocean, and this seems to work, but the time scale has to be explained. So Tom has done plenty of work on this, and he has developed simple models to provide more detail. So the simple model equation written is for the Southern Ocean temperature dTs in time varying with time with a relaxation or a oscillation time scale, proportional to minus TNT, obviously that corresponds to northern hemisphere temperature change, minus TST, which is the same as this one, so you know that there is a kind of exponential dependence there. So here Ts is the temperature anomaly in the Southern Ocean, and Tn may represent temperature anomaly of Greenland. And then you represent minus Tn is the temperature anomaly of the South Atlantic adjacent to the Southern Ocean. So you are taking the Southern Ocean, separating the Atlantic Ocean from it. So you're trying to go from the Greenland change to the South Atlantic. It's just a simple modeling trick. Assuming instantaneous seesaw. So you assume that the Southern Ocean and the South Atlantic are connected at a much more rapid time scale. Tau is a characteristic time scale for the heat equilibrium in the Southern Ocean. If TNT is given, so if we have some data for Tn in time, then using this relation we can compute the evolution of Southern Ocean temperature. Of course, the time scale, characteristic time scale for heat equilibration is unknown, but you have some idea from the data, right? So the data shows you this relation. So we can solve this equation by Laplace transformation of this equation. So TST can be written as -1 over tau, which is fixed, 0 to t. So you are integrating within that equilibration time scale in terms of the known Tn at t minus t prime with a lag which is shorter than the relaxation time scale, times e to the minus t prime over tau dt prime plus the initial temperature of Ts, because you are perturbing the initial temperature which is changing with the time scale tau as well. Okay, so meridional transport is transporting heat across meridional circulation, is transporting heat, so it's acting on initial time temperature in the Southern Ocean, which itself is not constant because you are changing the meridional transport, so you have to account for that as well. So that's a simple Laplace transformation solution of this equation. And the results show that high-pass filter time series of the temperatures in Greenland and Antarctica. So you are taking this and trying to predict Antarctic temperatures derived from ice cores. C is simulated temperature according to 9.2 with input A. So you are assuming Tn is given and you're trying to reproduce this. And the abrupt Danskard-Oeschger events of the north hence become manifest in the local isotope maxima in Antarctica. So A1, A2, A3, A4, these correspond to the northern hemisphere changes. As you can see, it's not always one-to-one correspondence, but there are many events that are identified. This is a figure from Tom Stoker's paper with Johnson. So basically, the idea is that this model can explain the observed relation between the northern hemisphere and the southern hemisphere, except that this works on a 1,000-year time scale. When tau is order 1,000, it works, but in the full ocean GCMs, this is a simple model. In a full ocean GCM, the time scales are more at 200 to 300 years, so you still have to explain why there is a difference of such a big difference between the time scale of heat equilibration between the northern and southern hemisphere in the simple model versus the ocean general circulation models, right? There is another interesting consequence of the bipolar seesaw which follows from the equation we saw here. Consider a very simple case of northern hemisphere temperature signal that has the shape of a periodic step function. So let's say the northern hemisphere is doing the abrupt jumps as we saw here, as we see here. So we can write it as a function TNT, temperature change over Greenland in time, as minus half delta t for some range of time scale, time periods 2I times t0 less than t less than 2I plus 1 times t0, and then it jumps to plus half delta, it jumps to positive and negative plus half delta t for 2I plus 1 t0 less than t less than 2I plus 1 t0. Okay, so let's make sure we didn't yeah, sorry, this is 2I plus 1 and this is 2 times I plus 1. Okay, just be careful. So assuming that the Southern Ocean temperature is 0 for simplicity, we get in this interval 0 less than equal to t less than t0. So I equal to 0, that just becomes 0 less than equal to t less than equal to t0. Then Ts over the southern hemisphere evolves as 1/2 delta t times 1 minus e to the minus t delta t, that's minus t over tau, sorry, which can be written with simple Taylor series as TST approximately equal to Ts at the initial time plus dTs dt, how it is changing in time, at time t0 times t, which is of course delta t over 2 tau times t based on this solution, which says that the southern hemisphere temperature is directly proportional to the jump in the northern hemisphere, but it corresponds to the relaxation time as well as the duration of the change. How the duration of northern hemisphere temperature change, how long it lasts, okay, which is a good approximation for the time period, which is much less than the equilibration time. So if you have equilibration time of multiple thousand years, then within that equilibration time you can still produce these short time scale abrupt changes. We find a remarkable linear dependence of the maximum southern ocean warming on the duration t0 of the northern hemisphere cooling. Okay, so t0 on the time period of change of the delta t in the northern hemisphere, you get a proportional warming. So less heat you transport to the northern hemisphere and cool the northern hemisphere temperature abruptly. So the heat transport is continuous, but a process of interaction between the glacier and the North Atlantic Deepwater Formation can create a jump. So the delta t is a jump, but there is a response in the southern hemisphere which depends on the duration of that jump. Does this work? Well, it turns out that it does. Linear correlation between the duration of the cold stadials preceding the Danskar-Dushkar events, the jumps, in Greenland and the temperature amplitudes of the warming in Antarctica. The numbers indicate the Danskar-Dushkar events in the previous figure we saw. This is from the EPICA community member paper. So this is EPICA some place that the name is kind of complicated. Okay, so you can look it up. And what is the temperature change happening there in the southern hemisphere, and how does it correspond to the stadial duration in Greenland? You can see that as the duration of the delta t in Greenland ice core increases, the jump in, or the warming in the southern hemisphere, increases. So there is a remarkably linear correlation between them. So just using all the data we have, we can build a simple model that explains this bipolar seesaw, including the abrupt changes in the north corresponding to amplitude of warming in the south. Okay, so obviously here some approximations have to be made, especially the relaxation time scale is kind of a tuning parameter that fits the southern ocean temperature to northern hemisphere changes. So you still have to explain the physics of those time scales. What are the processes by which the time scales are being determined? for this bipolar seesaw. So it's not a complete story, but it's a remarkable progress in explaining what is observed in the ice cores in terms of these abrupt changes and bipolar seesaws, all internally generated. Okay, so that's why they correspond to multiple equilibria in the climate system.